Hi everyone, and welcome to this tutorial video of the structural analysis of the Airbus A320 wing using Siemens NX Nastran. The Airbus A320 is one of the most famous aircraft used by various different airlines. We will assume a NACA 2412 airfoil for the design for the airfoil, and we don't really have the exact data for what airfoil is used, but NACA 2412 is a reasonable assumption to form the preliminary analysis. So what we're going to do is we're going to search for the NACA 2412 airfoil, which will bring us to this particular website. We'll go to airfoil tools website. This is how it looks like, and what we'll do is we'll try to plot the NACA 2412 airfoil. Here we can provide the system with different parameters for the airfoil, such as chord length. Say for example the chord length is 6.5 meters for an Airbus A320. We give 6500. The others are not as important for this example, but you can give different parameters based on your requirements, and then we click plot. Once we click plot, it plots the particular the required airfoil, and we can download the airfoil data in CSV format. We can also download the airfoil in .dat format as a data file. And then we can use the data points in x and y coordinates to plot the airfoil, and then eventually draw the airfoil on NX as well as the wing. However, this is not the most efficient way of designing the airfoil. So let me show you what happens if we use this particular method. Say for example, if we're using 40 data points, which is not a lot, but just for the sake of simplicity, we used the NACA airfoil generator to generate the data points for the airfoil, and then we plotted these data points. Now what we're going to do is we're going to try and create a spline by joining these points. However, you will notice that this is an extremely tedious and slow process, as you have to select every point after multiple clicks. So for example, I click this point, and then I click add new point, select the point selector button, select the point, click OK, and then repeat the process. Now, when you're trying to make an airfoil, you will have multiple points, not 40 points. You will have, say, 80 points or 100 points, 200 points. So it then becomes very, very impractical to use this method. We can use something that is a little bit simpler, a little bit faster. So what we do is we try and sketch, create a sketch along the plane of the data points. Say X and Z for this particular case. So what we would do is we would start connecting all of these points using a profile. One thing to note here is that the profile will be connected by straight lines. So the more number of points you have, the smoother the spline looks, and the more accurate it looks like an airfoil. However, this is not the best method to create the airfoil. So instead of using the profile method to create the sketch, what we would do is we would use the spline method. So let me just delete all of these straight lines. Yeah, so what you do is in the same plane you select the spline command, you click a data point. Yeah, this is just a more accurate way of selecting the point, just so you're not selecting something random. Click new, and then you click the point selector, and make sure you have make sure you have entire assembly turned on, so you can select points from a different file as well. And you don't need to have multiple clicks now. All you need to do is select all of these different points, and the spline will connect them automatically. And also you see we've got this thing called degree, which is the method of connecting the different data points. So if you have if you choose degree as 2, it will make a parabolic connection. If you leave the degree as 1, it'll be a straight line, and so on. So again, the more number of data points that you have, the smoother the curve, and hence more accurate the airfoil. Essentially what it would also mean is the smoother the flow of the air over the wings would be. So generally good practice, but as you can see, it is still quite tedious. So now that we have completed our airfoil, let me just finish the sketch here. Yes, so once we've completed the airfoil, there are multiple ways to create the wing. We can either extrude it. So let me just show you an example what happens when I extrude. So the total semi-wing span, let me just do it for 4 millimeters for now. So what you see is that it is not a very smooth curve. That's because the software interprets this as slightly rough around the data points, and it is going to give us inaccurate results. While it is okay for preliminary analysis, this is not a very practical method, and there's something we need to do about it, which makes more sense. So here at Engineering Tutorials, we've developed a tool for you which you can use to generate the airfoil shapes, the airfoil data points, which not only includes generating the airfoil and saving the data points, but also defining how many ribs you would like. So for example, let's consider the example of the Airbus A320. So this is the interface of the tool. You select the NACA 4-digit code, which is 2412 in our case. You select the total wings, semi-wing span of the Airbus A320, which is 16.955 meters. The root code is 6.5 meters, and it tapers down to 2.3 meters on the tip, and it consists of a total of 27 ribs. So we select, say, 200 points per rib to make sure that the airfoil profile is very, very smooth, and then all we've got to do is create on generate wing. So let's go ahead and do that. So what you see here is that we've got 27 ribs spanning across 16.955 meters, and this is the profile of the airfoil. We're assuming all of the ribs follow the NACA 2412 profile for simplicity, and what you can do is you can also export this as a step file. So let's go ahead and export this as step file here. Let's create a new folder called the Airbus A320, and let's save this file as and name it Airbus _A320. Let's yeah, so it's already saved the step file, and look at how convenient it becomes. Let's go ahead and open the step file in NX. Okay, so what you see here is that we've got the profile for the airfoil for each of the different 27 ribs, spanning across 16.955 meters, with the starting chord length of 6.5 meters, tapering down to 2.3 meters at the end of the wing's tip. Alright, let's go ahead and let's go ahead and make the ribs. So each of the ribs for the Airbus A320 will be assumed to be 0.2 millimeters, not 0.2 meters, sorry, 0.2 meters thick. We're estimating these values from a research paper, which I will link in the description box. Okay, so let's go to the extrude command. Okay, so we cannot select the curves altogether. So what we'll do is we'll set the in order to set the thickness as 0.2 millimeters, we will set the distance to 0.1 across each direction. Let's actually select the direction, the direction of the extrude first. It's the software is just a pain sometimes. Okay, so let's go to the extrude command. Let's specify the direction of the extrude as Y. Okay, so just select YC in the specify vector command. Now set the alright. Yeah, we still can't select all of the curves at once. Anyways, we'll do it individually. Just select the distance as minus 0.1 meters and plus 0.1 meters, giving a total thickness of the ribs as 0.2 meters. And now just select each of the curves individually. Unfortunately, the software isn't letting me select all of the curves together. Oh, it is. Okay, the software just decided to let me select it now. Well, okay, let's see. Oh, it seems to have run into some problem again. Let's see what's going on, because it was working when I was selecting them individually. Let's see what's going on. Okay, seems to create a problem somewhere around here. Okay, let's see what we can do here. Yeah, this doesn't seem to work. Okay, maybe we have to select them individually. Let's just choose the thickness as 0.1 E3 in each of the directions. Let's begin selecting the curves for now. Alright, yeah. Okay, it shouldn't be minus 100. Yeah, it should be minus 100, yeah, that's correct. Yeah. Let's select all of these curves individually. Now the system seems to be working fine. Probably the software doesn't want you to select all of the curves together, but never mind. It's just 27 of them. Not too much of a pain here, I suppose. But I'm going to see if there's an easier way for the future. So we select each of these curves, and the extrude command will then create these ribs. Let's apply and click OK. So what you see here is that we've got each of the ribs created for the Airbus A320 semi-wing. We don't have to specify any sort of distance for distance for the length of the wing, because the engineering tools wing generator software already took that into account, and it's created the ribs accordingly. So you can see the profile of the airfoils. They're all the same, just getting smaller, just getting tapered as we move along the wingspan. Alright, so now let's go ahead and create the skin going over these ribs to complete the wing. So doing that is slightly tricky, so pay a little bit of attention here. You need to be very careful how you want to make the skin of the airfoil. So the easiest way that I've found so far is that what we can do is we can scale the curve for the airfoil profile with the required thickness. So we will assume a thickness of 0.4 meters. This is again from the paper linked in the description box. So what we'll do is we'll scale it to be smaller just by a factor reduced by a thickness of 0.4 meters. So we go 6.5 minus 0.4 whole divided by 6.5. We want the scaling in X direction, we want the scaling in Z direction, but we do not want any sort of scaling along the Y axis or the spanning axis along the wingspan. So now what we see is we've got, let's zoom into this, yes, so we've got two curves. Looks like just an offset of the curve, which is the right kind of profile that we're looking at. Now what we need to do is we need to create a guide curve for our wingspan. So let's go ahead and select the tip of this particular airfoil. Okay, didn't select properly. Let's go ahead and do that. Yes, so we want to select the end point here to the end point on the tip of the wing as well. There we go. Alright, yeah, okay, so end point on the tip of the wing. Finish the sketch. Now we've got a profile along which we want to sweep this curve. Once we do that, let's go ahead and rename this the guide curve first. Let's name it, say, wingspan guide. Now let's go ahead and sweep this airfoil curve along the guide. So go to surface, select the swept command, and select these two particular curves. Let's just hide the ribs for now. So what you see here is we will first select this particular one of the airfoils, and see this particular section here. It determines how your taper is going to behave. So what we want is it should start at the given airfoil length and should end along a taper ratio of 2.3 divided by 6.5 for accuracy. Now what we want is we want another solid sweep. So we create we select the other airfoil curve along the same guide, same taper, and again 2.3 by 6.5 here. So we've got two solid bodies and we want a hollow body, so we'll perform a Boolean operation here. So we go to the subtract menu for a Boolean operation. We subtract this solid body from the outer solid body, and what we've actually got is an airfoil wing with 27 ribs and a skin. Okay, so now let's go ahead with the finite element modeling in order to perform the structural analysis. So let's go to application pre-post, select new FEM and simulation. The solver is Siemens NX Nastran. The analysis type is structural. Click OK. Okay, so now name this solution as cruise phase, for example. You can say anything, just say cruise phase cantilever, because this wing will essentially behave like a cantilever. Make sure the solver is SOL 101 linear statics. Now the first thing you want to do when creating a finite element model is that you want to work on the idealized parts. This helps you edit any sort of this helps you make any sort of modifications on your parts without affecting the original part, which is very handy if you're going for an iterative design process. So let's go ahead, open the idealized part. First thing you want to do is promote all of these bodies, so it creates so it sends an idealized part to the system. So any changes you make will only apply to these individual mid-surface biplane for these systems, ribs as well, individual parts rather. So let's go ahead and create a 2D plane for the skin itself. So the system is quite smart actually. If you just select the skin of the wing, it will automatically generate a shell body. Let's go ahead and click apply. So you see it's already created a shell, but we still have the solid bodies for the ribs. So the next thing to do is so go ahead and select each of these ribs. Hopefully you can select all of them together, but just to make sure that there are no problems. Sometimes the software tends to behave weirdly, but it's only software at the end of the day. So yeah, let's go ahead and select each of these individual ribs. Hopefully the software will detect and okay, so it did run into some problem when I selected these two particular wings, these two particular ribs. So let's see what it's doing. Let's see what it's done. Okay, for the last two ribs, what it's done is, because it was set to automatic for the mid-plane generation, it's detected the plane wrongly. Alright, so let's go ahead and fix that. Let's undo the last operation, and what we'll do is we'll select all of these ribs except for the last two, and then we'll do the last two ribs individually, just to make sure there are no issues there. Well, yeah, this is just a problem with software. Sometimes they tend to behave quite weirdly, but not the biggest of issues. We can always work around that. Okay, so you see, the minute we select the last one, it creates a problem. So we're going to deselect that, create these individual ribs. Now what we'll do is we'll select the other two ribs manually instead of going automatic. So let's see. So open manual face pairing, select the rib. So you see, the minute you select, the automatic pairing selects the wrong plane, the horizontal plane. However, you want the vertical plane. So let's go ahead and actually select the two faces of the rib. Okay, it's a little bit of a pain here. Let's see what we can do. Yeah, let's just select from the list. So we can select this particular face, then we'll go and select the other face. Let's see, yes, it's done. Now we also need to deselect the face detected automatically in order to make sure that it's still not taking the horizontal plane. So let's go ahead and deselect this. Okay, perfect. Let's see if we can select the other rib here itself. If not, we'll just do it individually. Where it looks like it's not very happy for us to do it in the same operation. That's alright, we'll do it individually. It's not a problem. Let's go ahead and do the same for this one. Alright, so again, what we want to do is select the, yes, so we select this face, and then we select the other face. Perfect. So now we've got all of these individual ribs enveloped by the skin of the wing. So now we've got our wing ready with the idealized part, with the idealized geometry. We can go ahead and start creating the finite element model now. So let's see. So select 2D mesh, and let's do the skin first, shall we? So let's deselect all of the polygon bodies, and let's only bring up the skin. Perfect. Okay, actually, you know what? Let's do the ribs first. So we make all of the ribs visible. So there should be 27 of them. So yeah, polygon body up to 56. That's all of the 27 ribs. Select this. Let's do automatic sizing for the mesh. It looks a little bit too big. Let's go 100 millimeters. Let's create a mesh collector. Let's call it ribs. Let's assign a material for all these analysis. We'll assume it's made of aluminium 6061. We will only do an estimate. So if you click OK, it will still take the correct thickness of the ribs, because if you don't provide anything, it takes the default thickness. However, we can always do 0.2 meter thick. Let's go ahead and apply the mesh. Okay, so it says there's some Jacobi errors, so we can actually look into the Jacobi error and make the mesh a little bit finer where we have these errors. But for now, we'll just skip this process and do it a little faster. So what we can do is we can just increase the mesh density here. So let's go ahead and then decrease the size of each of the elements. Let's say 50 millimeters for each of the mesh element size. Okay, there's still some errors, but for now let's just ignore that. This is just for tutorial purposes. Okay, yes, I can see that the mesh is not perfect because the idealized part was not created very well, potentially. Regardless, let's go ahead and create the mesh for the skin as well. So let's select both the faces of skin. Let's say 100 millimeters for the skin. Let's create a new mesh collector. Let's call it wings. Same material, aluminium 6061. Thickness is again 0.4 meters. Click OK, apply. Just waiting. Perfect. Okay. There are some small mesh creation errors. We can ignore that for now. So, let's go ahead and change the color of the mesh just so it's a little bit clearer for us to view. Let's say amber. Yes, it looks much better, much more recognizable. If you want a little bit, I don't like the green mesh, so this is just a little clearer for me. So I'll go ahead and make this purple. So now we have the finite element model created. Perfect. Now what we can do is we can actually connect the ribs and the skin with 1D collectors. but that's not the easiest thing to do, so we'll use a trick in the simulation itself and we'll avoid this. Alright, so let's head over to the simulation file. Let's open the sim file from the simulation file view. Now, as explained earlier, the wing behaves like a cantilever beam fixed at the fuselage. So let's apply a fixed constraint at the edge of the wing. Okay, let's do one thing. Let's hide all of the solid bodies. We only want the 2D bodies that we've created in the idealized part. So let's go ahead and select all of these edges. Make sure you've deselected any of the additional edges. Okay, click OK. So we have now created the constraint. Let's apply some forces. So let's go ahead and apply the downward force acting due to the fuel contained in the wings. So we've got about 3,000 kilos of fuel. This is acting downwards. So let's select this surface. Just make sure that the surface is selected. Now 3,000 kilograms of force acting downwards. So go to specify vector, select downwards, click apply. Now we need to apply the lift. So the Airbus A320 is supposed to have a maximum lift force of 70,000 kilograms. That means 70. We have 35,000 kilos of lift in each wing. So let's go 70,000 divided by 2. Again, acting on the bottom face of the wing in upwards direction. Now we also have the weight of the wing pulling it downwards. So let's go ahead and apply the gravity load. Just 1g for in this case, acting downwards. Click OK. Click solve. Okay, so there is some sort of error. Let's see what it says. Okay, so this is a common error that occurs in NX. It wants you to set auto MPC to yes. So okay, let's go ahead and edit the solution. Click edit and go to case control and the parameters. Look for auto MPC. Change that to yes. Click OK. Click OK again, and then solve it, and hopefully this time everything's going to be fine and it will run the simulation. One thing to note here is that we have not included the weight of the engine acting downwards on the wing, so we'll do that in the next tutorial. So let's go ahead and wait for the solution to finish. Okay, it's completed. Let's see if we've got some results here. Okay, it shows some error. Let's see what's the problem. Okay, so the problem is that the wings and the ribs, the skin and the ribs have no constraint between them, so they aren't connected. So the ribs basically are floating freely according to the software. So what we need to do is create some sort of connection between the two. So let's go ahead and delete any sort of 1D connections that we might have. What we'll do is we'll go and create a glue constraint between the ribs and the skin. So let's go with edge to surface. So let's select the inner faces of the skin as the target. Let's name this wing. Select OK. Go to the source. Let's just hide this. Let's just hide the skin. And yeah, just make all of these ribs visible. Okay, software is doing something weird. Okay, maybe again it wants me to do it individually. Let's see. Let's hide all of these solid bodies first. Okay, it's a little annoying, but let's hide them anyway for now. Okay, let's hide these. Select all of these edges, name them ribs, select OK, save it. So now we've got a glue constraint between the ribs and the skin, which means that the system assumes that the wing is so constrained that the skin is always in contact with the ribs, and they're immovable with respect to each other. Let's go ahead and solve it. So if my assumption was correct, it should give results this time. Otherwise, we'll see what's going on. Let's wait for the solution to complete. It's completed. That was relatively fast. Okay, so let's cancel this. Let's see if we've got results. Perfect. So we've got results this time. And this is the wing after the load's been applied in the cruising phase. So you see the wing slightly bends downward, which is the expected result. Let's try and animate this and see how it will look. So you see how the wings are trying to bend downwards. So we must. Okay, let's have a look at the stress first. So we have a maximum stress of just under 39 megapascals, which is way below the yield limit of aluminium A6061. We can let's stop the animation first. Okay, what's going on? Alright, so yeah, so the animation is stopped. So we see that we've got a maximum stress at the joint where the wings are connected to the fuselage, and again, maximum of let's use annotations to visualize the max and minimum stress. So you can see that the maximum stress is at the connection point, and the minimum stress is at the tip of one of the airfoils. Let's make the skin visible as well. So the maximum stress is at the connection point. If we look at the rotation, as you can see from the diagram, the tip of the wing is the most bent portion of the wing. So understandably, the rotation is maximum there. So the results are actually exaggerated by 10% for visualization, but if we change that to absolute value here, we see that the wings aren't actually bent so much. Let's make this the animation slightly smoother. Let's see how it looks after that. Perfect. Let's stop the animation, increase the visualization to again 10%. Let's run the animation, much smoother, and we see how the how the rotation contour is distributed along the span of the wing. Okay, so now let's go ahead and add the actual wing model to the analysis visualization as well. Makes it look much nicer compared to when you can actually compare it to how the original wing looked like. So let's go to edit post view. In the deformation, click show undeformed model. Select the color as, say, whitish gray, make it translucent. And now you can see how the original wing looked and how that deformed wing looks like. So you can do the same for rotation, stress, displacement, etc., etc. And you can see that if you select the deformation to be absolute, you can see that the wing isn't actually bending so much practically, which is what you would want from your wing. So if you liked the video, if you liked the tutorial, please give the video a thumbs up, comment if you have any doubts, please subscribe to the channel, and a more detailed analysis will be posted in a further video where we'll include the engine as well.